Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.4.3 on symmetric matrices. Now, do you remember what a symmetric matrix is? It's one that looks symmetric about the forward diagonal, like this. So we have a matrix here, and if we have an entry here across this diagonal right here, you have a symmetry. Another way of saying this is that if you replace or switch your rows to be columns and vice versa, so switching rows with columns and looking at that matrix would be taking its transpose. So A transpose is equal to A. That's another way of saying that a matrix is symmetric. And this little subsection discusses symmetric matrices a little bit. First, it gives some rationale for what we're about to consider. Like, let's suppose you're taking a matrix and raising it to a power like the fourth power. So, and suppose this matrix is symmetric. Then you could write it this way because A is equal to AT, A transpose, so you could write it that way. And in particular, when you multiply this matrix to a vector V, and suppose that you get 0, all right? All right. Now, if this is true, then in particular, if you had put this matrix, so V is like a column, and here this is like a row, right? But if we multiply this matrix to a matrix calculation, which is 0, you still get 0. But realize what this is. So this is like taking a column vector, this multiplication, and this multiplication is like a row vector. And this row vector is the same as this one, only just thought of as a row instead of a column. And when you make a matrix multiplication like this, it's like you're taking every entry and multiplying component-wise in the normal fashion for like taking a dot product between two vectors. So really this calculation is like this. You know what that means? If you take a dot product of two things and you get 0, that only happens because this is actually one of the things that can be useful in computing length of a vector. This only happens when the vector itself was a 0 vector to begin with, which means we actually have a squared times v is 0. So assuming that a to the fourth times v is 0 actually means a squared times v is 0 if a is symmetric. A similar idea actually holds if you just have a to any power. So you have if A is a symmetric matrix and you have A, it doesn't matter to any power like this, dot of vector is 0. So that actually will imply, via induction and some other considerations, that AV is 0 itself. So if A at the n is 0, that means that A must be 0. And that, or the A times V is 0. A to the n times v is 0, then A times v is 0. This is something that something that happens for symmetric matrices. Okay, so using that idea, let's see what that does for us. Well, let's suppose that we have some kind of matrix, and we look at its Smith normal form, or as we do some row operations with polynomials. So in a polynomial module, an Rx module. So we're going to be thinking of operations in here, and you somehow get this. Now remember that we actually determined that if you get something like this, then really if you just like take the least common multiple of everything you see right here, let's see, that actually will give you the minimal polynomial. So least common multiple is, x plus 4, x minus 2 squared. That would be like the minimal polynomial for such a matrix. Well, what if this matrix is also symmetric, let's see what would happen then. Okay, so then, well, let's just kind of look through what this really means. This is like a zero multiplier. So, like, so as it acts on anything, um, let's see, in particular, yeah, so b times anything here would be 0. In particular, if you have 0, 0, let's just kind of do that just for now, for convenience. And then anything here. So that means b times, well, in this component, that means b times anything will be 0. Well, b times, now in that component, actually, the only thing that survives in the matrix multiplication, let's kind of see that. So let's consider what we're doing. We have 0, 0, and then we have something here. So when you matrix multiply, this result will be like taking this and multiplying it to this column. And really all we'll be left with is 0, 0, whatever that was, times x minus 2 squared. And kind of what we want is this is actually going to be interpreted as 0 itself in order for that to work. So that means that x minus, that means that, okay, right in there, just gonna clear this and keep going here. All right. So x minus 2 squared times, okay, in particular, we could have just said x minus 2 squared times that anything in there was 0. All right. Well, and realize what x minus 2 is. If x is a symmetric matrix to begin with, then x minus 2 is also symmetric because you're subtracting off a matrix with 2's down the diagonal, and that's symmetric as well. And you'll get something symmetric. So you have a symmetric matrix times a vector, and it's going to be the 0 vector. So x minus 2 squared will also be a symmetric matrix times a vector is 0. So this implies, so this being 0 implies that this is also 0 because it's symmetric, right? So well, that actually implies that this is a 0 multiplier. So, but the minimal 0 multiplier that we actually found was up here, and this kind of contradicts that minimality in some ways. There's different various ways of seeing that or thinking about that. In particular, you think about determinants being preserved with these row and column operations. And the determinant here is a degree 3, and determinant here is a degree 2. I mean, there are some issues that actually happen, and with our merging stuff, things just don't really work well. The crux of the matter is it just doesn't really work. It can't happen if it's symmetric. You cannot get something like you can't get something like this. You have your 0 multiplier in the end that you actually get can't have any square factors down this diagonal. It only has to have factors of degree 1. So this would be okay, but then we would have to maybe have another factor somewhere happening, maybe an x plus 4 down here multiplied right here. Maybe that would be okay. So what we could have done here differently, we could have had a x plus 4 in this multiplier. All right, so we could have had something like that, and that would have been okay in the end, or we could have had like x plus 1 up here. But the crux of the matter is that in each of these diagonal entries, at least, you can't have any square factors. That's really what we were looking at. We can't have any square factors in each one individually. So, well, that actually brings up a point, because what if we were trying to find the minimal polynomial? Remember what I said, it was the least common multiple of these entries down the diagonal. So if we had like an x plus 4 down here, the least common multiple would actually be x plus 4 times x minus 2. Even though you see the product of the diagonal, you'd get a square, but that doesn't matter because we're looking at the least common multiple of that. And that would have been just fine. So that would have been okay. It's even okay if we have, in the end, if we kind of did some some operations, even if we had like an x plus 4 up here, that would still be okay, because the least common multiple of all this is still x plus 4 times x minus 2. So the minimal polynomial basically for a symmetric matrix cannot have any square factors at all. So that's the idea that we're getting from this. That actually has some nice consequences. And we'll just kind of come down here. All right, get to that point. All right, so here's just an example here and talking about how we can think about the vector space, which is, so the vector space R3 that we're kind of working with, and we're analyzing it with the matrix X. And notice that what we're doing is we're taking the, just to remind ourselves, we're taking this free module. So instead of R3, we think of polynomial ring 3. And we're modding out by the action of the matrix X. And we saw that's the same thing as like declaring something like this is like a zero multiplier. So that's kind of what we're working with. And let's just kind of come down here for a minute. So that's kind of like assuming like this is 0, and like when we're modding, let's see what this looks like. So this is like a 0 multiplier, and it's a 0 multiplier on, in fact, we can actually write that out. That'll be useful. So think about, we have, so this is acting on Rx3. So we're kind of modding out by the action of this on this. Now, in the first component, so something in here has 3 things, 3 different polynomials in a tuple, and the action of this matrix on it. And the first thing, it could be like anything, right? So when we're modding out by that, basically it's like we're ignoring, if you see a 1 here, it's like we're ignoring that entry. So we ignore that entry. Now in the second guy, we have polynomials and we're modding out by this. So in the second entry, it's like we're taking Rx and we're modding out by x minus 2. So polynomials that are multiples of x minus 2 go to 0. So that's what it looks like in that second entry. In the third entry over here, actually, I have it written right here. So the first entry is like gone. Second entry is like this. And the third entry is right here, like we're modding out by that. Now, you see what this is? If we mod out by x minus 2, it's like when we divide by x minus 2, we look at the remainders. Well, the remainders are just degree 0, because degree less than degree 1, and that's like real numbers. So basically, in this component, we just have real numbers. In this component right here, we think about modding out by a product here of things that don't share common factors by Chinese remainder theorem. That's like saying we can split that up further like this. But Rx and then cross Rx, and then here we're modding out by x minus 2. All right. So what we end up getting, and each of these in turn is just like R. So this is really like R cross R. Notice how many R's you have. So it's really like R3. So the crux of the matter is that we're describing our vector space R3 as split up into, as isomorphically as a, it's split up isomorphically as a cross product, or a Cartesian product of 3 different spaces, which are each isomorphic to R1. They're isomorphic to R1, but they have some particular meaning here. So, that's what our matrix has done. It's split up into 3 different things. So it can be acting on those 3 different subspaces. And in this subspace, this is interesting. When you're in this subspace, actually x, how does it act? Well, x actually acts exactly as 2 does, because x minus 2 is 0, which means if you multiply by x, it's like multiplying a vector by 2. That's called like an eigenvalue, and this is like an eigenspace. In this, now in this one right here, it's like x is behaving the same way as -1. And so it's like the eigenvalue for this space. So there's some subspace here, which has an eigenvalue of -1. If you're in here, any vector in here, if you multiply by x, it's like you're multiplying by -1. In this one, it's like you're multiplying, so that's a 2. It's like you have a multiplying by 2. So you have subspace here of dimension 1 where multiplying by x is like multiplying by 2. This subspace is like multiplying by -1. This subspace is like multiplying by 2. And the idea is that that we can, and that always happens for a symmetric matrix. And the reason why it always happens for a symmetric matrix, and the reason why we could do this, is because the minimal polynomial does not have any square factors. So we could actually use the Chinese remainder theorem in this one, and then this is separated from this because it comes from a different component, and everything works out nicely. So you can actually split it into what are called these eigenspaces. This actually gives us a nice way of studying a matrix and its powers. So let's take a look, and we just kind of discuss that a little bit. In fact, here, this is a little description that the eigenvalues that we get for a symmetric matrix always have to be real numbers. So you're welcome to look at that. So no complex numbers here as we go along in that way. Okay, so here, let's suppose we have this matrix. We compute the determinant of this, and we know the minimal polynomial divides it. Okay, and this is what we're getting. We're getting x minus 2, x plus 3. Okay, so if we just take this as our, just assume that's, it's like our minimal polynomial here. And in fact, we know that if we multiply this to anything, we get 0. Let's think about that. So there should be some subspace where x is acting like 2 and some subspace where x is acting like 3. So how do you get a vector that, let's look at this. Okay, a vector so that x is acting like 2? It's actually quite easy if you think about in terms of polynomials. And it's not always demonstrated this way, but this is rather simplistic. I mean, think about this. If you have this is like a matrix, and it's like a function, right? And the output of this function, if you apply this function to it, you're going to always get 0, which means you just take anything in the output of this function, and this is going to behave like 0 on it, meaning that x is going to behave the same way on it as 2 would, meaning that anything in the output of this function is what you'd call an eigenvector living in the eigen subspace of associated with the eigenvalue of 2. So so let's take a look at that as we keep going in the reading. All right. So v is in the range of a plus 3, so a is like x here, then this will be true. Okay, so let's think about a plus 3. A plus 3 is, we take the matrix A and just add 3 on the diagonals. We get this. That means 4, 2, and 2, 1. These right here are what you'd call eigenvectors for the matrix A with eigenvalue 2. Okay. All right, so that means in particular, notice that 4, 2 is a tag along to 2, 1. I mean, it's in the span of it. So really the eigenspace is one-dimensional. It's just generated by multiples of 2, 1. So we can kind of think about this. Matrix A times 2, 1, and we can check it out. It actually does behave just like multiplication by 2. Okay, so what we've just done is we've found, now this is important, finding these eigenvectors and eigenvalues. We'll see why this can help us quickly to determine powers of a matrix A that is symmetric. So, okay, so we have an eigenvector, we have the eigenvalue, and the eigenspace associated with it is just generated by a single vector, 2, 1. Now let's look at the next one. Okay, things with the eigenvalue of -3. Where is -3 coming from? It's coming from, well, look at this polynomial right here. -3 is the makes this part 0. And so we know that if anything in the range or the output of x minus 2, and by the way, this multiplication is is commutative here in this particular case. Okay, thinking of the minimal polynomial, x plus 3 times x plus x minus 2. I mean, we're just looking at powers of x and then constants. I mean, all those things commute very nicely. So we can think about this x plus 3 on both sides. Okay, so if we first run x minus 2, we're going, and we first run x minus 2, then anything in that output, x plus 3 would make 0, which means anything in this output, x behaves on it the same way as multiplication by negative 3. So we look at, so in this particular case, we look at the range or the output of a minus 2, and that's just the columns, okay, the span of the columns. Notice the span of the columns is the same thing as looking at the span of this one vector right here. So that means that this one vector right here is an eigenvector for the eigenvalue of negative 3. Okay. All right. Okay, so how can we use eigenvalues and eigenvectors? Well, here's a little description here, but I'll just kind of cut to the chase right here. Let's think about right here. Let's look at a matrix T. This matrix T, I'm lining it up with eigenvectors. So this is the eigenvector that we found for 2, and this is the eigenvector that we found with negative 3. So we line them up 2 and 3. Now, if we put the eigenvalues right here in a diagonal, 2 and negative, let's see, well, right here, 2 and negative 3, let's think about what's happening. So the matrix T, kind of what we're doing is, with the matrix T is, let's take E1. What does T take E1 to? So here's the matrix T. T takes E1 to 2, 1. What does A do? What does A do to 2, 1? It just multiplies it by 2. And then let's run T inverse, which would take, oh, this is nice because it's like E1 to 2, 1, and inverse will go backwards, but now we have a constant to go with it. So then it goes backwards, so it takes 2, 1 to E1, but 2 comes along with it. And the basic effect is of this composition of running the matrix T and then A and then T inverse is just to multiply E1 by 2. And all that came from putting the first column as that eigenvector. All right, and then just running A. So it's kind of nice. We just kind of come up with this matrix right here, T, and just looking at it right here. Now notice that's exactly what happens here. This composition, what did it do to E1? It took it to 2, 0. It just multiplied E1 by 2. So really this composition for the first column is just going to be E1 multiplied by 2. Likewise, this last column right here is just going to be E2 multiplied by negative 3, which ends up being a nice diagonal matrix. Now, if we rearrange this equation like this, we've just successfully written A as a diagonal matrix with zeros on the offset, with just a matrix T here and a T inverse here. And if we compute the inverse of T, which there's a quick way of doing that for 2 by 2 matrices, we could just switch these guys and just make the off diagonal entries the opposite signs, which is exactly what we do, and then we divide by the determinant, and that gives us our inverse very quickly. So we have matrix T, we have its inverse on the right side and T on the left side now, and then we have this diagonal, which associates, so these eigenvalues, so the first eigenvalue is associated with the first column eigenvector. Negative 3 is associated with the eigenvector right there. We have just successfully written A this way. Now, why is that useful? Well, let's call the middle matrix D. Let's think about what we can do. A squared, let's just write it out. And notice that when we do, these guys cancel in the middle, and we're just left with D squared with T and T inverse. And in general, A to the M is very nice. It's just this diagonal matrix raised to the M with a T here and a T inverse. Now, why is that useful? it's really easy to multiply diagonal matrices that are just diagonal like this, because the result is just multiplication component-wise of the diagonals. So just like this, it's like that. So we can actually come up with nice forms for high powers. So this is an alternative viewpoint from using modular arithmetic, but it is useful in its own right, and sometimes it's pretty handy. So in this particular case, like here, how would we compute a to the fifth? Well, we could just take this matrix to the fifth power, fifth comes in, make that a 2 to the fifth and negative 3 to the fifth, and then you're just multiplying through, multiply that out, you get a to the fifth. So this is actually the same result from previous example. So we'll go up there when we did in comparison to polynomial modular arithmetic. Right here, a to the fifth. And what did we do this time before? In this particular example, we found the determinant, and then we modded out. We took x to the fifth and looked at it, modded out by that determinant right there, and the representative was ax plus b. We can actually solve for a and b by plugging in 2 and negative 3 in this equation, and we end up getting the exact same thing, which is right here. And that concludes our little video. Thank you for watching.